Hello ladies and gentlemen, and welcome back to the 10th laboratory session for GTS 300. I hope you've all already managed to watch through the lecture which I just gave, which basically gave kind of a high-level overview of correlation. And basically now what we're going to do is we're going to go through a few examples within this R session very quickly to show you exactly what you kind of need to know in order to kind of excel on the assignment that's been set. Okay, so you need to download the code from MyMason, and then basically you need to open it up within your R session, and you need to install the lattice package if you've not already done that. Okay, so I'm just going to show you what to do here. You can press Control Enter on Install Packages, press Enter, and it's basically going to actually install what's required down here. So thankfully it's successfully installed. Once that's happened, we can then click Require Lattice, which just basically says go into my hard drive to get the lattice package and load it into my current R environment in order for us to use in this particular session. Okay. Now, what we're going to be using here is the environmental data set. So this is a pretty old one actually. So it's the atmospheric environmental conditions in New York City for 1973, and it's the daily measurements of ozone concentration, wind speed, temperature, and solar radiation between May to September. Okay, so it's 111 observations with 4 variables. The ozone concentration is the average hourly measurement in parts per billion. So the radiation, which is one of the column names in the data set, is the solar radiation in Langley's. The temperature is in Fahrenheit. It's the maximum daily temperature, and the wind speed is in miles per hour. Okay, so look, you've got the details here. If you want to take a further look at the data set, we can load it in here as env. So I've just said get environmental data, allocate it to env, and that just provides us with those columns that I already covered over here within the help menu. Next, we're able to actually extract some of those environmental columns. So here we've got the temperature and the ozone level, and basically we're able to put those into our global environment as vectors, as you can see here, for all 111 data values that we've got. Okay, so for temperature and ozone, I'm just printing them down here to the console so that you can see all of the data values. So the question is, let's just qualitatively look at whether these two plots are actually related to each other based on this correlation approach that we've picked here. Okay, so we've got ozone here on the y-axis, temperature here on the x-axis, and if I just open this up, generally there seems to be a bit of a weak positive correlation that essentially as the temperature increases, the ozone concentration also increases. Okay, and that's concerning because ozone can have some detrimental health effects if you breathe it in when you're down on the ground. So you don't really want large amounts of ozone being produced. Obviously, it provides a very important function up in the atmosphere to protect us, but also when it's down on the ground, it's actually quite bad for us, and that's why we kind of want to be aware of this. And basically, as the temperature increases, it looks here like the ozone concentration also increases. And obviously that's a concern for us. I just wanted to place this graph like this because actually in the homework, there were in the assignments that I set, there were a couple of people submitting graphs without actually providing labels or units for those axes, and that's actually quite concerning. So I just wanted you to basically in the next step of this practical, kind of pause the video, go into the code where I've placed plots here, and I want you to make sure that you're able to add the labels onto that plot function so that you can add in the ozone parts per billion and the temperature in Fahrenheit. Okay, because you should, following good scientific practice, never submit or release any type of graphic or graph that basically doesn't contain units. Otherwise, what are these units that we're measuring these values in? Okay, I mean, are they leprechauns? Are they meters? Are they feet? What are they? So they need to actually relate to something. Okay. So try replot that and add the axis labels on. Okay, I hope you all managed to pause the video and have a go at trying to replot that so that you can actually produce that graphic with the required labels on, and also, you can also work at trying to add a title, make sure it looks pretty for when you submit work to me, but also when you leave this class and go on into the future. So let's focus now on trying to create Pearson's R² by hand. So you'll remember that we covered this within the lecture, so we needed to first get this covariation metric, and then we're able to produce the R value that we want for Pearson's correlation coefficient. So using those vectors that we've got, we can now get the means for both the temperature and the ozone. We can just use the inbuilt mean function to place them into our environment. We can then take the standard deviation for those two different vectors for temperature and ozone and add those into the global environment. And then we can take the length of the temperature vector to get the number of paired observations that we have, which is 111. So now that we've got all of those, we can basically start to crunch through to get that R metric that we're interested in, okay? So let's just start with this covariance parameter here. So basically what we're doing is we're going to subtract the mean for Y from each of the other ozone metrics, and then we're going to multiply it by the subtracted X mean value from all of the other temperature values, okay? And then when we do that, these are basically the deviations from the mean. We're then able to sum them to get the covariance, which is what we're interested in, all right? So let me just have a look here. We've got a covariance of 24,367.28. And now that we've got that, we can basically move on from the covariance part and go into Pearson's product moment correlation coefficient estimation. So we want to now get this R value here. So essentially we're dividing that covariance value by the number of paired data observations that we have. And then we're dividing it by the multiplication of the standard deviation for X and the standard deviation for Y. And then this eventually gives us our R value, so we have a positive correlation of 69% essentially, so 0.69. It's positive, it indicates it's positive correlation, and obviously 1 would be perfectly positive, 0 would be no relationship between the two variables, -1 would be a perfectly negative correlation, okay? Now we are able to find a p-value for that. So remember, within this we can determine if an association exists between the two variables, and we have our null hypothesis, which is that we don't have any relationship, and we have our alternative hypothesis, which is there is a relationship. Basically we can get that t value, the test statistic, by multiplying r by the standard, the square root of n minus 2, and dividing it by the square root of 1 minus r squared. And then when we do that, sorry, this bit down here, we get a t-value of 10.01, so that's indicative of the fact that the p-value is going to be highly significant because it's a large t-value. So our p-value that we get is 1.97 to the minus 16. And just to pick up on some of the errors I saw in the assignments, remember this is scientific notation. So some of you were thinking, oh, it's 1.97, that's above 0.05, so this isn't significant. Obviously, this is just scientific notation. It's indicating where the decimal point is, this kind of basic value, and then you have what the following number of decimal places relative to that value, which obviously is minus 17. So we have essentially 16 other zeros on the other side of that decimal point. Okay, so that's quite a very significant result that we've obtained there. So just remember that you need to kind of convert into a normal number to interpret those values. We could just use the inbuilt correlation function here for temperature and ozone, and that provides an R of 0.69. So again, that's a positive correlation. Obviously, that's slightly quicker than doing the manual work that we did up here. Or you could use one of the inbuilt functions, core.test, which produces the Pearson's product moment correlation. You get a highly significant p-value again. And importantly, here it's trying to indicate that we basically have enough evidence to reject the null hypothesis and accept the alternative hypothesis that the true correlation is not equal to 0. So these are significantly different from what we would expect to occur at random. So basically, there's some sort of relationship between these variables. They are correlated, and the correlation coefficient is 0.69. So it's 69% variability 69% of the correlation is explained as a result of these two different factors. Okay. So look, let's move on now to Spearman's rank. So basically what happens if we have non-parametric data? Well, essentially what we can do is we can add a ranking into our data, okay? So we've got this env data set here, and we could go rank temp, and we could go rank env temp. Great, so now if we go into env, what we've got here is we've got a rank for each of those temperature variables. So from the smallest temperature, we've got a rank of 1, and then we go all the way up to the largest temperature here, and we've got a rank of 111, okay? So basically what I'm doing when I use the existing vectors that we separated out from the data set here, when we say rank like this, is basically saying find the rank for all of those temperature values, and it's going to give me this jumble of numbers, but what that's doing, as I showed you in the data frame, was just allocating 1 to the smallest value and 111 to the largest value. And then basically we can do that also for ozone, and we can give it to the correlation function, and we can say that the method that we want is to get Spearman's rank correlation coefficient, and that will give us the RS value, which is 0.77 here, so again quite a positive correlation. We can test rho to see whether or not there is a correlation between x and y. And when we do that, we get a highly significant p-value, so 2.2 to the minus 16, which means that there's clearly a relationship here, significantly different from what we'd expect in the null hypothesis, so where rho was equal to 0, and therefore at the 95% confidence level we can reject the null hypothesis and accept the alternative hypothesis, that there's a correlation between temperature and ozone. We can also test for directional alternatives, and this is important because a few of you did very well in the homework and you kind of got the right code and you got the right thinking, but actually what you've done is you'd applied the test, but then the test, you hadn't altered the alternative hypothesis. So for example, maybe you'd used a one-directional alternative hypothesis like this rather than a two-sided one, and therefore it produced an incorrect number because you'd unfortunately set the test up the wrong way around. So you need to just be aware as to which kind of direction you think that's going to be. If you don't know anything a priori, then you need to use two-sided, which may mean that it could be larger, it could be smaller, it could be positive, it could be negative. It's just different from 0. You're not saying which, it's just different. Or if you think you have some sort of understanding, like maybe you kind of intuitively think, oh, well, if temperature increases, then it's more likely to drive the chemical reaction that might produce ozone, and therefore we might have more ozone. Well, then you would basically say that you think it's going to be greater, because basically what you're saying here is you think it's going to be a positive correlation between these two variables, which is what you get here, okay? So we get the rho value of 0.77, we get a highly significant p-value. You could also do it the other way around, although logically that would be less sensible, because we kind of know that's not how it's going to work out, okay? So it gave you a p-value here of 1, and the alternative hypothesis is true, is rho is less than 0. So you need to kind of have some inbuilt logic as to which way you think that hypothesis is going to go, okay? Okay. Right, so that's kind of bringing to the end what we learned within the lecture and the correlation content that we covered this week. The other issue is that there was some important things that we covered in some of the other lectures when you were preparing for your midterm exam, right? So I just wanted to pick them up in one of these lab sessions, because obviously each of these individual tests that you're learning now, they don't take long to go over when you know how they're done and you've got the code in front of you. The thing is that you guys obviously need to learn those tests, which takes a lot more time. So I do understand that, whatever might take me 10 minutes to go over here may take you 45 minutes to an hour to really understand how that test works. But I do want to just cover this stuff very quickly, okay? So we didn't go over the Kolmogorov-Smirnov test, which was basically the test which you can use to see whether your data are parametric or not. which is always really nice, and I used it when I was in my undergrad as well, which is just basically as a way to say, oh look, to my statistics lecturer, my data do conform in the way I expected after applying the Kolmogorov-Smirnov test, and therefore justifies my choice of either using a parametric or a non-parametric test, right? So it's better than just kind of saying that it's normally distributed or it's not. So you have like a nice formal test. So essentially what we're able to do is we're able to see whether it differs from what we would expect to occur if the data was just normally distributed, thanks to kind of random variation. So you can look at the slides from lecture 11 if you want more information, but basically the null hypothesis is that the distribution is normal, but if we get a p-value below 0.05, then we would reject the null and accept the alternative hypothesis that basically the distribution is not normal, it is non-parametric, okay? So let's say that we've got this temperature data here, we're able to look at the test value here. So for the temperature data, the p-value is not below the 0.05 level, so we think that it's normally distributed. And if we actually look at the data, I agree with that. You know, you look at that, it's a bit skewed downwards to the right, but generally I think it's quite close to normally distributed data. And then when you compare that to the ozone data, I mean, the ozone data is significant, which means that it's not normally distributed. Which means that we need to reject the null hypothesis, accept the alternative hypothesis that basically the data here are non-parametric, okay? So these are not normally distributed data, and when you look at the histogram here for the ozone, you can quite clearly see that you don't have that bell-shaped curve that we're looking for in order to be able to use those parametric tests that rely on you having a normal distribution with equal variances, okay? Great, and then just to finish off, let's just focus a little bit on some of the other tests. So the chi-squared is the goodness of fit test that we use to basically look at count data that we had. So we're able to see if sample frequency counts are similar to expected counts, again in lecture 11. So let's say that we want to check if the expected number of people that commute to campus via certain methods is similar to what we actually sampled. So in this case, let's assume that we survey a bunch of people in GGS, major students, and then basically find out if they walked, took a bus, or drove to school in a car. And the results are that 10 walk, 10 take the bus, and 40 drive. So the question is, well, is this uniform? So let's input those different modes of transport into our memory, okay, in this vector called jog, and we can find the mean here. So we find that the mean is 20 for each of these buckets, and then we can get the chi-squared value, which is actually going to be 30 based on the expected number that we would occur, okay. So again, we can then look at the chi-squared value that we got, which is 30, using that probability chi-squared function, and it's giving us a highly significant result, okay, so 3.05 to the minus 7, which basically means that we have something that there is some sort of effect going on here. These results haven't just occurred by chance, okay. So let's just go back to where we looked at that, so the chi-squared goodness of fit test. So essentially what we did was we took the expected frequency count here, the observed frequency count here, we subtracted the expected from the observed, we squared them, divided them by the expected frequency count, and then we summed them up for all groups. And that's basically the chi-squared value that we got here of 30. And that 30 value relative to all the other points indicated that there's something significantly different with the results that we get rather than just random variation at the 95% confidence level. Okay, so let's just move now on to the final test that I wanted to cover, which is contingency analysis. So we may want to see if there's a relationship between transport modes and the major that people are taking. So in other words, is there a difference between the different majors? So in addition to those geography and numbers, we also sampled chemistry, mathematics. So the chemists had 30 people walking, 20 taking the bus, 50 driving, and the mathematicians had 20 walking, 20 taking the bus and 40 driving. So if we place those all into our memory, we're then able to create a data frame out of each of those different groupings that we had for the different modes of transport. And then we're able to basically just crunch through this equation that we've got for the contingency analysis to get this chi-squared value. So we need to get the number of rows and number of columns. That gives us the R and the K here. We then need to basically get the row sum. So this just summed across this dimension in the data frame here to give us the total for these rows. We then also want to get the total number of data points that we've got. So we summed the row sum in order to get the total number, which is 240 overall. We can get the expected frequency count by basically taking these values here. Sorry, let me just work out why that didn't run through. Oh, I'm sorry, I think I used it in the previous. Nope, maybe I didn't. There we go, so now we have a row sum and a column sum. My apologies, I don't know where that line of code went, but basically it produces our expected values down here. And then once we've got those, so we've got all of those matrix multiplication outcomes, and then we're basically able to divide it by the number of data points that we've got, and that gives us our expected frequencies. And then finally what we do is we subtract that matrix of expected values from the data values that we've got, square them, and then subtract and then divide by the expected matrix again, and this gives us a chi-squared value of 6.174359. Okay, so that gives us this outcome down here, but we do need to get the number of degrees of freedom. So we need to basically subtract 1 from each of the total number of rows and columns and multiply them, and here we get 4. And then finally we're able to stick that into our function here. So find the probability of the chi-squared value that we've got, CS, on the number of degrees of freedom. We get a p-value of 1.864999. So we do not get a value here which is significant, which essentially means that these data points that we've got could just have occurred by chance. They may be independent. It doesn't look like there's any sort of dependent relationship between any of these. Okay. Great, so you should have all of the code now and all of those tests in order for you to really excel if you're tested on them at some point. I think the key thing this week is for you really to just get your teeth into the correlation part and make sure that you get your assignment submitted, as that's going to be really the next thing that you need to deliver. I think that in the following lecture I'll give you an overview about what's going to happen in the actual in the exam. So I'll give you the regression lecture, and then I'll cover some of the topics that I'm expecting to test you on. So that should really kind of set you up to perform really well. But then I think the only thing that's left for me to say is, well, thanks for tuning in, and I hope you manage to have a nice week off or doing whatever you are doing during the Thanksgiving recess. And I hope you manage to have some quality time with your family or your friends, whoever you're spending it with, please make sure that you kind of come back refreshed and ready to kind of grab the last 2 weeks of the semester and really kind of push forward and perform to your very best. Okay, so thanks a lot for tuning in today, and I'll hopefully get a chance to see you all soon. Thank you. Goodbye.